Welcome back to multivariate calculus. In this video, we're going to be looking at the equations of planes. You're familiar already with the basic idea of a plane from Euclidean geometry. In Euclid's original definitions, a line was the simplest object which contained any two given points, and a plane is the simplest object containing any three given points, not all on the same line. In the usual interpretation, a plane is a flat surface that extends indefinitely in each of two directions. The screen that you're watching this on, or the paper that you're taking notes on, are great approximations of planes, or at least finite regions of a plane. We're going to be looking at things a little bit differently. Instead of thinking about the objects on a plane as being defined in and of themselves, we want to define the plane based on a perpendicular vector or a normal vector. We use the terminology of normal and perpendicular interchangeably. It's one of those annoying things in mathematics we can't decide on a single name. There are some distinct subtle differences if you study analytic geometry or algebraic geometry in detail, where normal or perpendicular should apply to the situation are slightly and subtly different. Understanding that differences will be on the scope of this course, and to be perfectly honest, will be on the scope of any course that I've ever studied myself. So I'm not going to try to make that distinction for you here. Instead, I want to think about a picture. If I get my head out of the way here, if we're thinking about a plane, two dimensions, somewhere in three-dimensional space, what I want you to think about is if I have a perpendicular vector, I'm going to call it n. I'll put a hat on it because it's going to be most convenient when this is a unit vector, although it doesn't have to be. And let's name that point where we are drawing this vector n as x naught, y naught, z naught. And then the point that we care about, x, y, z. All right, so x naught, y naught, z naught, and n, which is going to have some components. Let's name those components. Might as well do all the naming now. All right, vector n with components a, b, and c, and a point x naught, y naught, z naught are the definition of the plane. For any other point, x, y, z, the only way for x, y, z to be on this plane is if the vector from x naught, y naught, z naught, the point that we already know about, to x, y, z is perpendicular to n. If those two vectors are perpendicular, then the point in question is on the plane, because the definition of the plane is perpendicular. So if I draw a vector in there, it automatically fits into that. If I draw the vector and it's not perpendicular, The only possibilities are that the vector is pointing up out of the plane, or the vector is pointing down out of the plane. Anywhere along the plane will still be perpendicular. Oops, that's not where I wanted to go. And so thinking back, we know that two vectors are perpendicular if and only if their dot product is equal to 0. That's why the dot product was so useful in the first place. And we know, given 2 points, that the components of this vector are the difference in the x-coordinates, the difference in the y-coordinates, and the difference in the z-coordinates. All right, so just filling that in, we now have an equation for a plane. Might be a little bit nicer to simplify this, right? We know how to take the dot product of two vectors, multiply the x components, a times the quantity x minus x naught, multiply the y components, b times the quantity y minus y naught, and multiply the z components, c times the quantity z minus z naught. And any value of x, y, and z that satisfies this equation is a point on the plane. Any value that does not satisfy this equation is not a point on the plane. We've now established the equation for a plane. Before I do anything else, I want to jump over to GeoGebra. There's the button I wanted. And you can see that I've got a lot of stuff going on here on the left-hand side. I've set up a couple of sliders for A, B, and C, and then for X naught, Y naught, and Z naught. Why A, B, and C came out backwards, I'm not entirely sure. GeoGebra does weird stuff sometimes. And then I've written in the equation of a plane. If I expand that out, you can see it's exactly the equation that I had written down. And then I've also done a little bit more work here. I've found the point x naught, y naught, z naught. And then I found another point, x naught plus a, y naught plus b, z naught plus c. And the reason that I found that point is that the vector ABC is the vector between these 2 points, and setting it up like this will give me the point starting at x naught, y naught, z naught. So if you look at the coordinate axes here, you can see that there is a plane and there is a vector pointing out of the plane. And so if I play around with these sliders, we can see what each of these parameters does to the plane. I'm going to play with x naught, y naught, and z naught first because I think that's the most straightforward thing. X naught slides the plane around left and right. Well, along the x-axis, which is currently pointed left and right. Y, the axis which is mostly pointed front and back right now. And you can see that the plane slides mostly front and backishly. And then Z naught, which is currently pointed pretty well up and down. If I play around with this slider, will in fact slide the plane up and down, although it's not obvious to see that if you're not paying attention to where the vector is laying, just because of how GeoGebra cuts off the plane. I think it makes the most sense if you actually watch the point on the z-axis. Notice how the z-axis suddenly starts to appear and then disappear. And you can almost trick your brain into convincing yourself that that's the plane going up and down. But the fact that it's getting cut off at the extremes and you're not noticing a difference makes it a little bit harder to see. Then the interesting things are the vector parameters a, b, and c. If I grab point A, you can see that that is kind of twisting the plane around. B is also twisting the plane around in a slightly different manner, but kind of the same idea as A. And then C is tilting the plane upward and downward. All right, you get a lot of overlap between these because, again, a normal, a unit normal vector is generally appropriate. So having the magnitude of these be 1 is common, but if we don't have that, everything still works. All right, but we can see here the equation of a plane. We can see a little bit playing around with how that vector is pointing about, and everything kind of sort of mostly makes sense. All right, so diving in, when we're talking about planes, one of the things we're going to need to do is be able to write equations of planes. I've already mentioned that the usual geometric definition is that a plane is the simplest shape which contains 3 points not all on the same line. So here I have 3 points that are definitely not all on the same line. 1, 0, 0, 0, 1, 0, and 0, 0, 1. And I want to try to write the equation of the plane that contains all 3 of these points. All right, jumping back over to GeoGebra here, I've set up a graph where we can see the 3 points in question along with the plane connecting them. And yes, you can see the solution over on the left-hand side of the screen, but just ignore that for a little bit. Let's focus on the 3 points. Point A, 1, 0, 0, point B, 0, 1, 0, point C, 0, 0, 1. In order to write the equation of a plane, we just saw that we need to have the equation of a line which is passing, or which is perpendicular to the plane, or a vector perpendicular to the plane, and we need to know one of the points that contains the plane. And finding a perpendicular vector is a little bit challenging. But we can set up, at the very least, a couple of vectors. If I scroll down until I can find vector from a point, we can find the vector that goes from point C to point A, for example. Maybe, come on, from C to A. Okay, it doesn't want to do that. Let's go and set that up algebraically. We want the vector from C to A. And we want the vector from C to B. And we've drawn in two vectors here. We could have chosen to set this up in any order, but I think drawing the vectors from C is the nicest illustration of what's happening in this particular application. A normal vector, a perpendicular vector, is going to be perpendicular to each of these two vectors. So finding those vectors and finding the perpendicular is going to be our tool of choice. All right. So we're looking at any possible arrangement. I went from C to A. So I take the component by component of C minus A is going to be 0 minus 1, which is negative 1, 0 minus 0, which is 0, 1 minus 0, which is 1. And then vector V, I chose C minus B. Again, any combination here would work. That's just the one that I happen to choose because it looked the nicest in the picture. But we'll take the x components. 0 minus 0 is 0. 0 minus 1 is negative 1. 1 minus 0 is 1. And our goal is to write vector n, which is perpendicular to both u and v. And once again, thankfully, we've developed a tool for doing that. It's called the cross product. Before I continue on here, I want to stress one more time. I could have chosen to set up vectors u and v as going between any combination of two of the 3 points in any direction, as long as I'm not drawing between the same 2 points twice. I'm including one of the points in each of the vectors and the other 2 points, one in each vector. However I arrange that, whatever order I do, it won't give me the same value for vector n, but it will give me a parallel vector, two vectors that are in proportion to each other. And that's all we need for these purposes, for the purposes of writing this equation. All right, but we are going to be taking a cross product. We set up a cross product. My favorite notation is the matrix determinant. First row is going to have the unit vectors, I hat, j hat, k hat. Second row is going to have the components of vector u, negative 1, 0, 1. The third row is going to have the components of vector v, 0, negative 1, 1. And I break that down into the cofactors. I hat times the 2 by 2 matrix, if I remove that first row and column, 0, 1, negative 1, 1, minus j hat times negative 1, 1, 0, 1, plus k hat times negative 1, 0, 0, negative 1. And multiplying this out, I'm going to end up with 0 minus negative 1, which is 1 I hat. I'm going to end up with negative 1 minus 0, which is negative 1, so minus negative 1 j hat. And then negative 1 times negative 1 is 1, so I get plus 1 times k hat. A very boring vector n is going to be I hat plus j hat plus k hat. I'll take it, it works. All right, so looking at the components of this vector, A is 1, B is 1, C is 1. And then the components of the coordinate we're looking at, we can choose, again, any one of the three. 1, 0, 0, 0, 1, 0, 0, 0, 1. I've been doing most of my work centered around 0, 0, 1, so that's what I'll choose here. But again, it doesn't matter at all. So I have A, which is 1, times x minus x naught, which is 0. I have B, which is 1, times y minus y naught, which is 0. I have C, which is 1, times z minus z naught, which is 1. And that should be equal to 0. Cleaning up here, I get x plus y plus z minus 1 is equal to 0, or more simply, x plus y plus z equals 1. All right, there's our equation of this plane. Another thing that we can do with planes is if we have multiple planes, the intersection of those planes will form a line in space. All right, so as an example, let's take a look at this situation. I want to find the parametric equation for the line formed by the intersection of the planes x minus 2y plus z equals 0 and 2x plus 3y minus 2z is equal to 0. Oops, I don't need myself in the way. Once again, before we do anything else, I'm back here in GeoGebra, and I have these spinning because I think seeing this from a couple of different angles is what's going to really start to help you understand what's happening. We can look at the two planes, we can see what's going on. One of the things that I want to point out is that the intersection of these two planes includes the origin, which we can figure out looking at the equations. Because we have no constant terms in the equations, we know that each of these planes contains the origin. If the plane is not in the origin, there needs to be a constant term, a term that does not have a variable somewhere in the equation. Generally, it's going to be equal to something other than 0 on the right-hand side, but that doesn't necessarily have to be the case. All right, so we can look, we see that the intersection of these two planes looks like it should be a line. There's a pretty nice indication that it's going to be a line that is tending mostly upward in the z direction. It's going to have a much larger z component than x or y components. The rest of it's going to be a little bit trickier. We can try to look at this top down. Sometimes that helps. All right, we can also see here that it's going to be a lot more in the y direction than in the x direction. I can't find a good angle. There we go. There's a pretty good angle of showing how steep it is in z compared to x. So I expect that the parameter on x is going to be relatively small. The parameters on y and z are going to be relatively large. There are a couple of different geometric tools that you can use to think about the equation that we're going to end up with here. But I think that the easiest way is to just dive in algebraically. If I get my head back out of the way, we have here a system of two equations in three unknowns. We can solve that system. Now, there's more unknowns than there are equations, so we know that there's not going to be a unique solution, but that's a good thing here. We are hoping to get a result that involves variables. We need the equation of a line, infinitely many solutions. All right, so we're going to use the method of elimination. We can choose to eliminate however we so desire. What I see right away is if I take that first equation and multiply both sides of the equation by 2, I get 2x minus 4y plus 2z is equal to 0. And then I leave the second equation alone, 2x plus 3y minus 2z is equal to 0. If I add those together, I get 2 plus 2 is 4, negative 4 plus 3 is minus 1, 2 minus 2 is 0, 4x minus y is equal to 0, or y is equal to 4x. All right, there is one simplified equation that we're going to be using in our solution. But we need two, so we need more work to be done here. Take this equation, plug it back into one of the original equations. It again doesn't matter which one we choose, we just have to choose one. I like that first equation. Z is in its simplest form there. But notice that if I plug in, I have x minus 2, and instead of y, we're now calling it 4x, plus z is equal to 0, which means that x minus 8x plus z is equal to 0, negative 7x plus z is equal to 0, z is equal to 7x. Right, there's my second equation. And with that, we have everything we need. My goal is to write a parametric system, x of t, y of t, and z of t, that will satisfy these two relationships. The way that I've done this, I've set this up so that y and z are both functions of t. So if I go ahead and choose a very simple function for x of t equals t is about the simplest function we can use, and then just substitute in. Y is equal to 4x, but x is t, so y is equal to 4t. And likewise, z is equal to 7t. That should give us the system that we're after here. So I get my vector valued function that I usually use to write parametric systems. R of t has components t, 4t, and 7t. And let's jump back over to GeoGebra, where we have our coordinates, or our two planes still graphed here. And let's go ahead and put in our system. The x component was t, the y component was 4t, the z component was not 8, 7t. And if I hit enter there and graph this thing and move the graph around a bit, we can double check to verify that yes, in fact, this particular graph of this particular line falls right along that seam where the two planes intersect each other. All right. That's pretty well all I have for this video, so let's wrap up with a problem for you to try. Two different tasks that we've talked about here. Let's go with the simplest one. I guess the earlier one. I'm not sure that it's simpler. I would like you to write the equation of the plane which contains the points 1, 0, 0, 0, 2, 0, and 0, 0, 3. Then use GeoGebra or similar software of your choice to verify your result. Plot the 3 points, plot the plane, and make sure that the points do in fact fall inside of the plane. All right, see what you can do with that one, and I'll see you in the next video.